Hi, welcome to the supplemental video for Chapter 4, Series Circuits for the DC Fundamentals class or DC Circuits class. Yesterday, when we were working through the lecture in the PowerPoint, what I found was some of my exercises that I used to have in the PowerPoint are missing. And of course, I didn't have time to knock them out real fast. So I decided to do a supplemental video today where we work through some of the problems when we have unknown values. And you'll run across problems like this in the class and from here on out, so it's good to work a few out. First thing we're going to do, though, is we're going to review the characteristics of a series circuit. The first of which is the total resistance is equal to the sum of the individual resistor values. It's real simple. It's a series chain, and the idea is we are able to express the series circuit as a single resistor simply by adding up all the values. The next characteristic is that current is constant in all parts of the circuit. Once again, you only have one path for the electrons to follow. Therefore, those electrons are going to be flowing at the same rate. Doesn't matter where you are, how many resistors you've got in line, they're going to be moving at the same rate. Third, total voltage is equal to the sum of the individual voltage drops in the circuit. Each resistor, since it has its own unique value and the same current, it is going to have a different value of voltage drop. So basically we're changing the amount of potential energy seen by the other resistors in the circuit each time we go through another resistor. Finally, the power dissipated by the circuit is going to equal the sum of the power dissipated by each individual resistor. Since we've got different voltage levels being dropped at each resistor, and we have the same current, then we're going to have different power levels being dissipated by each resistor. So the total power dissipated by the whole circuit is equal to the sum of the individual power dissipations. So those are our four basic characteristics of a series circuit. Now let's take a look at one that has an unknown value. And as you see, we have a series circuit. We can see that it's got a single path for current to flow. There's no side paths, there's no alternate paths, because current will take the path of least resistance, but there's only one path here, so it's definitely a series circuit. We've got R0 at 5K ohms, R1, which we have no idea what it is, R2 at 3K ohms. Now, in addition to that information, we also know that R0 drops 6 volts. So its IR drop at that point is 6 volts, and our total voltage is 12 volts. So let's find R1, our total, and the voltage drop at R3. And one of my my pin pad just disconnected itself. Okay, I'm back again. So we're going for the value of R1, the total resistance value, and the voltage at R3. And believe it or not, this is quite easy because we're given a lot of information here. Now let's back up a slide and review these characteristics again. Resistance is the total of all the resistance. Current is constant. Now this is a big hint right here. That is one of the most important characteristics we've got. Current is constant. Total voltage, sum of all the voltage drops. Total power, sum of all the power dissipation. Now, we know current is constant, so if there's any way that we can figure out what the current is through the circuit, with this information, we can figure everything out. Well, we just happen to have a point here where we know both the resistance value and the voltage drop at R0. So let's apply Ohm's law. Now remember, the voltage at R0, not the total voltage, but the voltage drop at R0 is equal to the circuit's current times the resistance at R0. I don't need to put that extra R in there, do I? So times the resistance at R0. Well, we know the voltage. We know that we have some current. And we know the resistance. So now our only unknown left to us is the current at R0. So once again, according to Ohm's law, voltage over resistance is going to equal the current. So do the math, and what you're going to find is current is equal to 1.2 milliamps. So let's first think about R1. Well, we know that the total resistance is equal to the sum of the individual. So if I come up with the total resistance and then subtract the value of R2, and that should be R2, not R3 there. Subtract the value of R2 and the value of R0, that can only give me the value of R1. So how do I find the total resistance? Well, I know what the total voltage has got to be. I know what the current running through the system is. So total resistance is equal to total voltage over current. So 12 volts divided by 1.2 milliamps, or 0.0012, volts divided by 0.0012 equals 10k ohms. So now it's a simple matter of subtraction. 10k minus 3k minus 5k. Okay, R1 is going to equal total resistance minus R0 minus R2. So 10k minus 8k, R1 is equal to 2k ohms. So there's a value for R1. There's the value for total resistance. And the voltage drop at R2, well, that's a simple matter of current times resistance. So 1.2 milliamps times 3k times 3k equals 3.6 volts. Now if I wanted the voltage drop at R2, or pardon me, R1, I could either multiply current times resistance, or I could take total resistance and subtract R0 and R2. Pardon me, total voltage, and subtract the voltage drop at R2 and the voltage drop at R0. But 2k ohms, or 12 volts divided by 2k ohms, what am I thinking? That 1.2 milliamps, there we go, 1.2 milliamps times 2k is going to equal 2.4 volts. And if you add them up, 6 volts plus 2.4 plus 3.6 is going to equal 12 volts. So there's your check. So once again, we kept in mind the four main characteristics, with I as a constant being an important piece of the puzzle. We looked for where we had the most information that could give us I, or some form of I. And that turned out to be R0, where I had voltage and resistance. So I could apply Ohm's law for this isolated spot. Now remember, there is a difference. When you're talking totals, the total voltage means the voltage for the entire circuit, the resistance for the entire circuit, and then current. But when you're just talking an isolated component, you have to apply the values for that component. So there is a difference between the total current for the whole, the total voltage for the whole circuit, and then the voltage for an isolated component. So your totals versus your individual components. And this is where people usually make their biggest mistake, because they try to apply total voltage to a single component, and you can't do that. Total voltage is for the entire circuit versus the voltage drop for a given resistor. All right, where once again our numbers should come out to be about the same, but the values we're given are in terms of power at R0. Once again, we're going to solve for current, we're going to solve for R1, and we'll solve for total power. Well, in this case, we have a power formula. Okay, power at R0 is equal to the current times the voltage drop of R0. But we're not given voltage drop. We're not given the current. So we're working in terms of power and resistance. Well, we have a formula for that too. Because voltage equals current times resistance. We've got voltage there, so voltage is equal to current times resistance. So So power at R0 is going to equal the current at R0 squared times the resistance. Now, we're interested in what the current is here, so we can figure out what the voltage drop is. We're interested, and we're also interested because that current is going to give us the total current for the circuit, which is going to allow us to figure out the total resistance, which will give us the resistance at R1. It will also allow us to come up with the total power. So that means the current is equal to the square root of power over R0. So I is equal to the square root of 7.2 milliwatts over 5k ohms. So 0.0072, that's 7.2 milliwatts, divided by 5,000 equals 0.000144. We'll take the square root of that, or current is equal to 1.2 milliwatts. Oh, pardon me, milliwatts. 1.2 milliamps. Now remember, this current applies to each resistor, not just R0, because current is constant. So I now have the current for all parts of the circuit, and I can go ahead and figure out what I need. I want total resistance. Once again, total resistance is voltage over current. So 1.2 0.0012 1 over x times 12 equals 10,000, as we expected. $10,000. So I've got 5K and 3K, 8K minus 10,000. That's going to give me 2K for R1. Power total is I times V. Total current in the circuit times the total voltage. So 12 times 0.0012 equals 14.4 total power, 14.4 milliwatts. Once again, keeping in mind our characteristics where current is an important part. Taking what is given us, where the most information is, and then using our Ohm's law and the power equation. So Ohm's law and the power equation, which allowed us to calculate current without any knowledge of what the voltage drop was here. Just using power and resistance, we were able to calculate what the current was and then work through each one separately. Start at one spot and then work your way through one step at a time until you get to your destination. Don't try to take it in as a whole, ever. That's how everything works in electronics. Okay, here we have a 4 resistor string. And of course it is a series string, only one path for current. But in that series string now, we have a reference point. Remember, this reference point is nothing more than a reference for making measurements. It says, this is where my ground probe goes. A meter has 2 probes. It's got a positive and negative. This is where the negative probe goes. If the negative probe is closer to the plus side of the battery or power source, then your measurement is going to turn out negative. If it is closer to the negative side, then your measurement is going to turn out positive. It's as simple as that. These voltage drops, nothing here is going to change as far as its absolute value goes. Okay, here I have another 10K string. All the values are given to us this time. So I've got 10K ohms and 10 volts. So now let's just apply Ohm's law real quick and find out what the current's going to be in the circuit. According to Ohm's law, current is equal to voltage over resistance. My total voltage is 10 volts. My total resistance is 10K ohms. It's going to come out to be like 100 microamps, I think. Or maybe 1 milliamp. Yep, 1 milliamp. Okay, so my total current through the circuit is 1 milliamp. So now I can figure out each of my voltage drops. 1 milliamp times 4 ohms, that's going to be 4 millivolts. Let's check that out. That's what I thought. $10 volts. Oh, 10K. Ha, 10 ohms. Pardon me. I've been working in thousands so much lately, I didn't even read my own writing. So whoever's out there right now scratching their head, you have every right to be. 10 volts over 10 ohms. So I equals 1 amp. There we go. So R0 has a 4 volt drop. R1 has got a 3 volt drop. R2 has got a 2 volt drop. And R3 has got a 1 volt drop. You add them up, you're going to find that they equal 10 volts, as they should. Now we'll call this point A. Call this point B. Call that point C, D, and E. Now it depends on where I'm taking my measurements. If I am measuring A to E, and when I say A, that's where the positive probe goes. E is where the negative probe is going to go. So if I'm measuring A to E, I'm going to see a drop of 10 volts because I'm measuring right across my power source. If I measure points A to C, well, my negative probe is on point C. So my positive probe is on point A, my negative probe is on point C, and the ground tells me in this situation, if I'm referencing point C, then that has to be where my negative point is, or where my negative probe is. So A to C, my voltage drop is going to equal 4 volts plus 3 volts, a 7 volt voltage drop. If I'm checking points C to D, well, that symbol there is telling me my negative probe has to be there, which means my positive probe has to be on point D, which means my meter, because all of a sudden my negative probe, my negative reference point, is actually more positive than my positive probe, I'm going to read minus 2 volts. Now the absolute value being 2 volts isn't going to change. It's just going to be the meter reading showing me a negative 2 volts, because that guy says my ground point is going to be higher than my positive probe point. Volts C to E is going to equal minus 3 volts. Once again, because point C, having the ground point on it, says I have got to be measuring from this point. That is my reference. That is my negative reference, which is more my negative reference is higher than my positive probe. However, the absolute value, it may read negative 3 on my meter, but the absolute value of this voltage drop of R2 and R3 does not change. It is still a total of 3 volts. If I'm measuring point D to E, well, I'm no longer forced by that symbol. Point D to E, I can go back to that, and it will be. It's only when your measurement point includes the ground symbol do you have to put your negative probe on that point. I hope I'm making that clear. But you can see it is straight Ohm's law, just applied to individual resistors. So the voltage drop we measured here was current times R0 that gave us V0, and so on through each resistor. Alright, let's work one more here. And this one I kind of just threw together. This time I see I've got 4 resistors, one completely unknown. I have 2 resistors that all I know about is their resistance rating. And then I have one that gives me my resistance rating and a power rating. At the same time, I don't know anything about my voltage source, except I know that the whole circuit is going to dissipate 30.7 milliwatts. So, where do I have the most information? Right here. So I'm going to use this, once again working using resistance and power, and from those two I can figure out what the voltage drop is there, and I can figure out what the current is there. Now, I'm not real concerned about what the voltage drop is right away, because that doesn't affect anything but this one resistor. However, what affects the entire circuit? Current. So, how do I get current out of resistance and power? Well, once again, mixing Ohm's law with the power equation, we know that current equals the square root of power over resistance. So that is going to give me the current for the entire circuit by knowing the power and the resistance of the single resistor. So let's bring the calculator back into play here. And power is 0.000737 divided by 450, which equals 1.64 micro. Now let's take the square root of it, which comes out to 1.2. Well, how about that? Closer to 1.3, but we'll say 1.28. Yeah, 1.28 milliamps. Okay, knowing that I have 1.28 milliamps, and that equals total for the whole circuit, and knowing that I've got a total power dissipation of 30.7 milliwatts, I can once again just go back to the power equation. So voltage equals power over I. So power over current. We'll take our current, invert it, and multiply it times power. .0307. There we go. Equals, there we go, 23.9889. I'm going to call that 24 volts. So voltage equals 24 volts. We know all the other values, so we can easily figure out R2 by dividing voltage by current. So clear. 24 divided by 0.00128 equals 18.75 K. Now it's just a matter of subtracting all the other resistor values to get R2. So 18.75K minus 3.6K minus 450 and minus 10K equals 4.7K ohms. Now we have the current, we have all the resistances, we have the voltage, so we can figure out the individual voltage drops if we want. We can figure out how much power each resistor is going to dissipate. We can figure out the rest of the characteristics all we want. But once again, we had to start somewhere. So we start at one resistor and then work our way outward. And that's it. If you run into problems working through your exercises and stuff, let me know. I'm here to help. I'll be here tomorrow night or Wednesday night from 7 to 9 p.m. Central Standard Time. Come into my virtual office and I'll work you through problems. I am available if you really need help. You let me know and we'll set up a special appointment time to get you the extra help you need. Don't get too frustrated. Don't panic. It just takes being familiar with Ohm's law, power equations, and then the characteristics of series circuits. And the characteristics are, once again, resistance is the sum of the individual resistance. Current is constant in all parts of the circuit. Total voltage equals the individual voltage drops. Total power dissipation is equal to the sum of the individual power dissipation. It's as simple as that. So, go ahead and go back to your reading, work through some of the problems, work the problems in the back of the book, practice, 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 because that's the only way you remember everything. And I will see you again in the next lecture. Bye.